You may recall that I was in the process of checking what I needed in terms of capacitors for the SX62A, and in keeping with being a good Santa Claus, I made a list and checked it twice. These are lists from two different SX62 document sets. Turns out that the capacitors match up precisely, at least with regard to the paper and electrolytic capacitors. And when I say paper, I'm talking about the ones that in the list are stated as molded tubular. Right there you see the designation molded tubular. Those are just basically paper and should be replaced at some point. But in the process, I then went through and gathered up what I think are all the capacitors I'm going to need. And they basically fall into four categories. Three different values of these 630 volt capacitors, that's these, the yellow ones, and then the safety capacitors that you need across the AC line. So you may ask, why am I wasting more time on all of this? Why not get on with replacing capacitors? The reason is that my philosophy is to try to get the set to work first with its existing capacitors, if you can do that. Then replace capacitors in one section at a time, testing after each replacement. So, for example, if you've replaced a capacitor or a bunch of capacitors and all of a sudden the set doesn't work, you have a limited area that you have to check to see what it is you did wrong. In the process of that, however, the first step is to get the set up and running, and I would like to at least test the capacitors in the set and see how likely are they to withstand an initial power up on the B+. You may recall that my original power up, I only set up the set without the rectifier tube. That reminded me of something. In fact, from an old TV book, in this Gernsback Practical TV Troubleshooting from the, I think, early 60s, there is a circuit shown here for a capacitor leakage tester. And I thought it might be nice to put that together to kind of go through and do a quick leakage check on all of the tubular capacitors and maybe on a few of the electrolytics, although this doesn't work quite as well for electrolytics. Which then reminded me of a capacitor leakage tester that I built, in fact, back in, I think, 1959 or 1960, looking a lot like this thing. We'll talk about this in a second. Out of an article from Popular Electronics. Well, as you know, things go when you get nostalgic. I thought, well, maybe I'll go try to find that Popular Electronics article and see if I can compare the one in the Gernsback book with that, and so on, which led me to this website, AmericanRadioHistory.com. And on this website, they have a treasure trove of old radio and TV magazines, a few books, lots of stuff. Now, it ranges over things from broadcasting magazines, but the ones I was most interested in are the ones that they call their consumer magazines in the technical section. I was able to find the exact article from the original Popular Electronics, and here it is. And if you look at the box, you'll see that it bears a striking resemblance to the box I built. That is, it has a switch, has a neon bulb, small differences. I used an NE2, this used an NE51, and I used an NE51 in my original. In this one there's a push button switch. In mine there is a toggle switch. I'll talk about why in just a second. But basically, when I finished this, I realized that although I built the box before I found the article, when I found the article, the changes I had made were so close to this original article that it occurred to me that nostalgia is not just a something to play around with. It also can sometimes help you. For example, in the original Gernsback book, the input resistance was 2.2K. I changed it to 3.3K because I seem to recall that number as being in the original. Turns out in the actual Popular Electronics article, that is what is in the circuit. So here is the circuit. You'll notice on the upper left here, 3.3K. I used 1N4007s instead of the old original Sarkis-Tarzian rectifiers in the article, partly because I don't think you can still get those. I used 22 microfarads instead of 10 microfarads for the capacitors. That just gives you a little bit more voltage, not a lot. And then I used an NE2 instead of an NE51, and instead of 100K in each leg, I put 150K in this leg alone, just to save a resistor. But basically it's the same thing. The way this works is it's basically two halfway rectifiers stacked on top of each other, so that this half of the circuit charges this capacitor to approximately the peak value of the AC line, which is about 140 to 150 volts, maybe a little more, depending on how much the load is. And this side charges this capacitor to a negative equivalent amount. So if you have 150 negative here and 150 positive here, that gives you 300 volts across the whole thing. 300 volts is a nice test voltage for the SX62 and for many receivers of this type. It's a little high for an All-American 5, where the average capacitor rating is 160 or 200 volts. But in the SX62, most of the capacitors have 600 volt ratings, so 300 volts is a good test. And so now let's actually test this box out and see how it works on a couple of capacitors. Here's the box hooked up to an 11 meg input digital multimeter, and you'll notice that the voltage indicated is 245 volts. And you'll notice that the light is on dimly. When the switch is in the off position, the leads are shorted. That's to discharge the capacitor in the circuit before you apply voltage. It's also to make sure that the leads are completely safe when you're making connections. When the switch is in the on position, there is 245 or 250 volts on the leads. It's relatively low current, but nonetheless it can give you a little bit of a tingle. Better to leave it in this position. And the reason that the original had a push button switch was so when you turn loose of the push button switch, it would automatically go back to shorting the leads. Now, a couple of things I will point out. If you need a bit more voltage, what you can do is use one of these transformers. This is a 2-to-1 step-up transformer. So let's put that in the circuit and see what happens. Now I have the doubler transformer in place, and you'll notice we're getting 570 volts roughly out of the same unit. So if you want to test capacitors like 600 volt units up near their peak, what you can do is you can buy one of these little step-up transformers. People use them where they have a piece of equipment from abroad, like a shaver, some very light, low power device that maybe they bought in Europe, and it runs on 240 volts. So this steps up the standard American 115 or 120 volts to 240 volts. And as you can see here, it also gives you a much higher voltage. I'm not going to use this for the SX62 because remember, all I'm really going to do with this is use it as a quick check of the capacitors in the set to see which ones are likely to load down the B+. Once I have determined that, I'll go through and replace what I have to get the SX62 B+ to come up, and then I will leave the rest of the capacitors in there, hopefully get the set sort of working, and then start on the wholesale replacement of capacitors, testing after each section. So that's kind of where I'm going. But let's see how this little unit works on some actual capacitors first, so you get an idea of what it might be useful for. I've connected a 600 volt 0.05 microfarad capacitor from this period, that is the 1950s. This actually was a 1950s capacitor. And now let's see how it checks on the checker. Now, for a paper or a low-value capacitor, what ought to happen is the light ought to blink once as the capacitor charges, and then it ought to go out, indicating that there's no leakage. And there you see you got a flash. And even though I leave it in that position and it's continuously applying 300 volts or 250, the neon light stays out. Do it one more time. You see the flash, and it stays out. Now let's put a not quite so good capacitor from the same period on the tester and try it. You notice that the light stays on. That indicates that this capacitor has some amount of leakage. Now, this particular tester is very sensitive. I have tested it against a pair of 20 meg resistors in series, and it will detect 40 meg of leakage, that is the equivalent of a 40 meg resistor, in parallel with a capacitor. What that tells us is that that first capacitor we checked has more than 40 megs of resistance to 250 volts. But this one is probably questionable, although the light is not fully on, and we'll show you that in a second. Now, if the capacitor were a dead short, you would have the light on all the time. And you can see a little of what it looks like there. It's fairly bright. Also, one thing that this shows you is that you don't have to worry about the test lead shorting while you're testing. There's enough internal impedance in this tester that it doesn't draw very much current. So at any rate, that is that. Now you might ask, well, what about electrolytics? So let's hook up one of those. Now I've connected a 1 microfarad 450 volt electrolytic. When you do this, you do have to observe polarity. obviously the negative lead has to go on the minus marked lead, and the positive lead, in this case the red lead, has to go to the other one, that is the one that's not marked, which is the positive lead. So now let's see what happens when we turn on, and I'm going to turn off the lights here so you can see the bulb a little better. And you see it comes on. Now the capacitor has charged, but it's leaking a little bit, it's having to recharge. But notice that as time goes by, the blink rate gets lower and lower and lower. This is a good electrolytic. It takes very little current, and even though we're putting 250 or so volts across it, very little leaks through the dielectric. In fact, less leaks through once the capacitor is charged than leaked through on this capacitor, which is just an ordinary paper. Now, you don't need to observe polarity on this one, but this is how I've spent the last couple of days getting ready to test the capacitors in that SX62. So the next step is to take this little capacitor tester out there, run it through the SX62, at least for the capacitors that connect to the B+ line, and see which of those, if any, I'm going to have to replace first before I do an initial power up with the rectifier tube installed. So that'll be in the next segment. I hope you'll pardon if I add just a little safety note at the end. I was going to actually say this at the beginning and forgot to. But if you're going to build this unit, a couple of suggestions. One is, you may notice in the original article, there is a terminal strip, and everything is tied down firmly inside to the terminal strip. You need to make sure that because this uses AC right in off the AC line, it can be dangerous, and you need to provide for some safety features. One is this resistor, that is the series resistor in line with one of the AC line values, is to limit any downstream current. And the reason I upped that to 3.3K, which is what is in the original article, is to cut down any chance of there being any current that could be pulled out of the AC line. The second thing I did is I used a polarized plug. That is a plug in which one side is the hot and the other side is always the neutral. In the old days, that wasn't possible. And then I made sure that the hot lead is the one coming through the 3.3K resistor, and the lead that connects to most of the circuitry is the neutral from the AC line. The third thing that I did is, you may or have noticed, this is an unusual plug. This is actually a cord off of a Christmas tree light string that burned out some years ago, and I saved it because behind that little door are some fuses that protect the everything downstream in case you get a short downstream in the box, or somehow in wiring it up you get it backwards or whatever. The fuses will blow in here rather than taking down your AC wiring or blowing the breaker in your garage or wherever it is. And finally, if you can, you should test it out first on something like this. This is a variable auto transformer. Actually, it's an isolation transformer that's variable, and you can raise the voltage slowly from virtually zero, watching how much current the unit draws. And if it's drawing too much current, figure out what's wrong with it before you crank it all the way up to 120 volts. The point is, be safe if you're going to build one of these. Follow the directions in the original Popular Electronics article. You can download that from AmericanRadioHistory.com. That's all one word. And Look under Popular Electronics, and as I say, I believe I recall it's the December 1959 issue, but you should be able to find it without too much trouble. It's a really good site, and I'm thinking of donating both, if I can, a little money and definitely some magazines that I have that they don't have yet. So I'm going to contact them and see if I can donate some magazines for them to scan. It says that you can do that, so I don't know the details yet. Anyway, so enough digressions. Now we'll get on to the SX62. In the course of the nostalgia overload that the AmericanRadioHistory.com site brought to me, I found the original or an original advertisement for the tube tester that I've been using here. This is the original TE15 tube checker. This particular advertisement is from the 1961 Lafayette radio catalog. Also, I found the key set that you use for the Hallicrafters knobs, and earlier I think I said it wasn't a spline. It is a spline key. I found this set online for very little money, and I will tell you that if you look online and you find these sets selling for $30, $40, look around some more. You can get them for about $8 or $9 for a whole set. I think that's what I paid for this, and because I ordered it with a few other tools at the same time that I could spread the shipping over, I think the total cost to me was maybe $10 for this whole set of spline keys. Now, you only need one for the Hallicrafters knobs, but if you try to buy that online, most people are charging $25, $30 just for the one spline key kit. If you look for a Hallicrafters knob key, if on the other hand you just look for a spline key kit like this from Bristol Wrench, you can get the whole set for about $9. Well, enough of that. The next thing I'm going to be doing is testing these capacitors. And you may notice a few of them look a little ripe. Some of them look okay. One thing that I did want to mention is you may want to get a hold of a copy of this book, Allied's Electronic Data Handbook. It's available online. I think if you just put this into a search engine, you can find it. It's available in PDF. And the reason is that in the back, it has the color codes for the old capacitor types. These are the old paper capacitor color codes, and they're very similar to resistor color codes, but there are some differences, and it does help to have all of this information, including this little chart down here that shows you things like the voltage ratings and other things that are not in the resistor color code. But basically it's the old starts with black, brown, red, orange, yellow, green, and so on for the various numbers, and the stripes read from one side to the other. There is usually an offset, and you read from the stripe that's closest to a wire and read toward the center, and then usually there's a tolerance or voltage rating or something at the end here. At any rate, if you get a copy of this Electronics Data Handbook, if you're doing a lot of old radio work or old TV work, there's a wealth of information in here. Color codes for transformer leads, replacements for tubes, and so on. So, but I've delayed long enough actually testing a capacitor, so let's do that and see what we get. I've hooked on to that capacitor, and for purposes of these kinds of tests, what we're looking for are pretty much dead shorts. Now, on this one, when I turn the tester on, you may notice that you get a continuous light. Now, I'll need to check the circuit to see if that is normal or if that's because that capacitor is shorted. The reason that I picked that particular capacitor is it had a kind of waxy coating on it, as though maybe at some point in the past it had overheated, and several in this region appear to be like that. So let me try another capacitor, see if we can find one that will test good. Okay, here is a capacitor, and I have the box set up across it, and you'll notice that it reads low leakage. That's compared to what a short would be. That is what you should get on capacitors in those parts of the circuit. Now let me get a schematic out here. Pause this for a second. Okay, it turns out that the capacitor that I am testing right now is this one, which you can see is off of the screen grid of this IF amplifier tube. And it has a large resistor in series or leading back to the B plus, or the screen voltage, and nothing else attached to it. That's one reason that the leakage is showing lower than it is for in other words, less leakage, higher resistance than it is for some of these others. Depending on where you probe in the circuit, for example, if you try to test in circuit for the leakage of, say, this capacitor, well, of course it will work because there's a coil connected across it, which has very low resistance, maybe 5-10 ohms or so. So if you put the capacitor across, capacitor checker across here, you're going to get what appears to be a dead short. It's not necessarily the capacitor. However, I think one thing that this has shown me is, in my zeal to resurrect what turns out to be my very first successful construction project back in 1958 or 59, I guess it was 59 when I built the first box. Not this particular one, this is a new one. I think I may have gone a little overkill here, because it's clear that almost every capacitor in this set is going to test bad on this, at least in circuit. I think what might be better would be to use an ohm meter to go through and see if there are any really bad capacitors. I mean, those that indicate very low resistance, and use the variable transformer to make up for the fact that I can't really test in circuit these capacitors. This has always been a problem, by the way, is how do you test capacitors in circuit, and there were lots of different attempts. The biggest problem is if you test using a modern multimeter, it only applies 4, 5, sometimes 9 volts to the capacitor, and in this old tube equipment that's just simply not enough. You got to put a couple of 100 volts on a capacitor to know that it's going to hold up. So I think, however, since this has not turned out to be a particularly successful experiment, what I'm going to do at this point is wrap up this video, work out a different way to go through testing these capacitors, do that so that I'll be ready to start the next video with an SX62 that is ready for its first true power-up, that is a power-up with B plus applied. I will point out that these boxes were very useful back in the day, but only in a limited number of circumstances, because they detected very, very low levels of conductance or leakage. In other words, very high resistance still showed up as leaky. They were really most useful in the television sets of the day in areas like the sync sections and the sweep sections and sometimes the IF amplifiers, testing, for example, coupling capacitors, where there was 250 or so volts on one end of the capacitor and the grid of a tube on the other end. And under those circumstances, if you had very much leakage in a capacitor, you could be pretty sure that it was going to upset the bias of the circuit. And so while these units are useful, they're not as useful for the application that I had intended here, at least in my opinion. So I'm going to go a different route, but for now I'm going to wrap up this video and hopefully, as I say, be ready to turn this set on for real when I start the next video.